Hi guys, welcome to Math TV with Professor V. In this video, we're going to cover Chapter 12 on inferences for population proportions for introductory statistics. And we're starting off with section 12.1, confidence intervals for one population proportion. So before we get started setting up confidence intervals, we're going to have to go over some new notation that we use when dealing with proportions. Up until this point, we've been working with confidence intervals and hypothesis tests for the mean of a population or sample, mu and x bar. So now let's see what we're going to use when we talk about proportions. P, we use lowercase p as the symbol for the population proportion. And then p hat, you see how we put a little hat on him? Oh yeah, how cute. That's the symbol for the sample proportion. And you do say p hat, okay? I'm not making this up. So we define p hat to be x over n. X also could be referred to as f, depending on your textbook. It's the frequency. And q hat is equal to 1 minus p hat, okay? So q hat is basically the complement of p hat. And again, x is the number of sample units that possess the characteristic of interest. It could also be the frequency. I think that's kind of what our book likes to use at the moment. And then n is the sample size. So let's just warm up using the notation. Little example here, it says, in a recent survey of 200 Americans, 62 were found to be dieting. Oh my. Find p hat and q hat, where p hat is the proportion of Americans on a diet. So to find p hat, we're going to look at how many in our population, or in the survey, excuse me, in the sample had the characteristic of interest. So how many people were dieting? 62 of them. And I'm going to divide that by n, the total, which is 200. Okay, don't rush for your calculator. We don't need it. Look, this reduces. I can divide numerator and denominator by 2. That's 31 over 100. And then 31 divided by 100 is 0.31. So p hat is 0.31. And then q hat I find by just taking 1 minus p hat. So 1 minus 0.31, which gives us 0.69. Okay, we're going to need both p hat and q hat and p and q when we set up these confidence intervals. So when we talk about the sampling distribution of the sample proportion, we basically want to know, what sort of confidence interval would make sense to use when we're talking about proportions. Is it the z? Is it the t? So let's talk a little bit. So for samples of size n, the mean of p hat equals the population proportion mu sub p hat is p. So what that basically says is the sample proportion is an unbiased estimator of the population proportion, and the standard deviation of p hat equals the square root of the product of the population proportion and 1 minus the population proportion. This is what your book likes to call it at the moment. Instead of 1 minus the population proportion, I just like to use q, okay, divided by the sample size. And p hat is approximately normally distributed for large n. So here's the setup for our confidence intervals. I think it's going to be easier for you guys to think of it this way than using the formula from the book. You have p hat minus, notice this is normally distributed, so that's why we're using z sub alpha over 2. Okay, and then here is our standard error, basically, or standard deviation, square root of p hat q hat divided by n. And just make sure that np hat is greater than or equal to 5 and nq hat is greater than or equal to 5. Okay, good. Now some terms to know. The maximum error of the estimate, denoted by capital E, is the maximum likely difference between the point estimate of a parameter, so that's p hat, and the true value of the parameter. The maximum error of the estimate is also sometimes referred to as the margin of error. So here's the formula for the margin of error, or E. Notice it's z sub alpha over 2 times the square root of p hat q hat over n. And that's exactly what we saw up above for the confidence interval, yes? This is E this is E. So again, you can set up your confidence interval with that same format. If you just want to think of it this way, that you have P hat plus or minus E. And that's consistent with how we've been setting up confidence intervals this whole time. So I wanted to do just a couple by hand, okay, so we can get into the groove, and then we'll look at Statcrunch in a little bit. 1A, a random sample of 205 college students were asked if they believed that places could be haunted, and 65 of them responded yes. Estimate the true proportion of college students who believe in the possibility of haunted places with 99% confidence. All right, so let's figure out what N is and X. The sample size was 205, so that's N. And then how many responded yes? 65. So then P hat is going to be 65 divided by 205, which gives us 0.317. And then Q hat is 1 minus 0.317. So we have 0.683. Okay, good. Now we're going to set up a 99% confidence interval. So remember, if we're working with a normal distribution and 99% confidence level, then Z sub alpha over 2 is equal to 2.58. Because that corresponds with alpha being 0.01. All right, so now let's go ahead and construct our confidence interval. So remember, the format is going to be P hat plus or minus the error, which is Z sub alpha over 2 times the square root of P hat Q hat over N. Okay, so what do we have so far? So P hat, that's 0.317 plus or minus 2.58 times the square root of 0.317 times 0.683 over 205. And then just punch this all in the calculator. You should have 0.317. Don't actually round this. I'm just telling you what's on my screen so far, 0.084. But what I do is I just leave this in the calculator with all the decimals, you know, continuing, and then I add 0.317 to it, so it's as accurate as possible, and then I'll subtract. So you should have for the lower bound 0.233, and for the upper bound 0.401. All right, good. Let's summarize the results. So one can be blank confident. So what was our confidence level? 99% confident that the population proportion of college students who believe that places can be haunted is between blank and blank percent. Okay, so since they said percent, I'm going to change both of these values from proportions to percents when I'm summarizing, just because that's the word they used. So let's use, that would be 23.3 and 40.1% based on a sample of, what was our sample? 205 college students. Okay, and then what is the amount of error for the estimate? Round to 3 decimal places. Well, we already have that. Remember, error is Z sub alpha over 2 times the square root of P hat Q hat over N, which was right here. And I know that that's 0.084. Okay, if you didn't have that, say you had done this problem in Statcrunch and you needed the error, you could just add these two values together, or take their difference, subtract them and divide by 2. Because basically you have here, think about how your confidence interval is. Here's your P hat, here's P hat plus E, right? And then you have P hat minus E. So if you want to figure out E, just take the difference, upper limit minus lower limit, and then divide by 2. Okay, last part of this problem. According to Time magazine, 37% of college students believe that places can be haunted. does this seem reasonable based on your estimate? So let's look at our confidence interval. Okay, the interval starts at 23.3% and goes up to 40.1%. And Time Magazine reported 37%, and that does lie within our confidence interval. So that does seem reasonable. I'll say yes, because 37% lies within our confidence interval. Okay. How are we doing? Good. Should we do another one? Of course. How fun. Okay. Example number 2. A survey of 500 workers showed that 45% belonged to a union. Find the 95% confidence interval of the true proportion of workers who belong to a union and summarize the results. Okay, so 500, what's that? That's our N, right? That's our sample size. And they told me already 45% belonged to the union. So what they did was they didn't give me X. I don't need it. They just straight jumped and gave me P hat, which would be 0.45. Isn't that interesting? Okay, so, you know, they're spicing things up. Just stay with it. Q hat is always 1 minus P hat. So 1 minus 0.45, that's 0.55. And they want a 95% confidence interval. So that tells me Z sub alpha over 2 is 1.96. Okay, so here we go. We'll have P hat plus or minus the error, which is Z sub alpha over 2 times the square root of P hat Q hat over N. And then P hat we have is 0.45 plus or minus, this is going to be 1.96 times the square root of 0.45 times 0.55 over N. That's why they had to give us N, because we needed it right here, you see? Okay, good. Then it's calculator time. If you keep getting the wrong stuff in your calculator, watch your parentheses and stuff, especially underneath the radical and when you're dividing. That's most likely where you're going wrong, is that you're not entering in and closing your parentheses properly for the calculator to understand the order of operations. But unfortunately, I can't see you and see what you're doing, so you'll just have to wait till I see you in class, and if I'm not your teacher, then I'm so sorry. Hang tight. Okay, 0.044. And lower limit should be 0.406 and upper limit 0.494. There's our confidence interval. Okay, so let's summarize now. One can be 95% confident that the population proportion of workers who belong to a union is between, and then again, see how they added the word percent? So I'm going to change both of these values to percents in my summary right now. So that would be 40.6 and 49.4%. And this was based on a sample of 500 workers. Okay. Now we're going to talk about sample size. And the size of the sample needed to make an accurate estimate depends on the amount of error, the confidence level, and the sample proportion. And we've talked about sample size before in previous chapters with different confidence intervals. So now we want to revisit that topic when we're making these confidence intervals for proportions. So remember, this was our formula for our standard error of the estimate, E equals Z sub alpha over 2 times the square root of P hat Q hat over N. If you rearrange and solve for N, which we've done before, so I'm not going to go through the steps again, it's pretty similar, we end up with the following. So N equals P hat Q hat times Z sub alpha over 2 over E squared. This gives us the formula for the minimum sample size needed for an interval estimate of the population proportion. So two big things to take away from this. Since N represents a minimum sample size required for a specified amount of error, we will always round the value of N up to the nearest whole number. So if from this formula you get something like n equals 14.000001, you have to round that up to 15. Because if you round down to 14, error goes up. So think those two quantities are inversely related. Error goes up as n goes down. Error goes down as n goes up. Okay? So if you have any little decimal carryover, gotta pop n up to the next integer. If some approximation of p hat is unknown, or is known, excuse me, then you're going to use it to find n. However, if there is no known approximation for p hat, use p hat equaling to 0.5. Why? Because that's going to give you the safest estimate. That's going to overestimate or give you the largest possible error. If p hat is 0.5, then q hat is 0.5, and that's the maximum of two numbers. That's the maximum product of two numbers between 0 and 1. Yes, we proved that in calculus. So anyways, just take my word for it for now until you want to study optimization. I'll link the video here. Maybe you want to read it. Okay, let's continue then. We'll work with sample size, okay? Good. Are you going to remember the formula? You don't need to memorize anything in my class. You can use a note card. Let me write it down here. N equals p hat q hat z sub alpha over 2 over e squared. That way we can refer to it while we do these problems here. Okay, so it says, a recent study indicated that 29% of the 100 women over age 55 in the study were widows. How large a sample must you take to be 90% confident that the estimate is within 0.05 of the true proportion of women over the age of 55 who are widows? Okay, so 90% confident, what I basically need to do to figure out n is get the p hat, get the q hat, get the z sub alpha over 2, and get the e. So let's make our list here. Where are all these values? Don't get overwhelmed when you read a problem and say, there's too many sentences, I can't handle it. Yes, you can. Suck it up. Okay, so p hat, it's right here. 29% of the 100 women were widows. So p hat is 0.29. Q hat is 1 minus 0.29, so that's 0.71. Z sub alpha over 2. Well, they want us to be 90% confident, so that corresponds with 1.65 for z sub alpha over 2. And E, how much is the error? It's right here. They want us to be within 0.05 of the true proportion. So that's your amount of wiggle room. That's your error. Okay? So N is going to equal, I'm looking up here now at the formula, substitute everything in. 0.29 times 0.71 times 1.65 divided by 0.05 squared. This one I'm going to redo really quickly in my calculator. So what I'm doing is I take 1.65 divided by 0.05, square that, and then multiply that by 0.71, and then times 0.29. Oh yes, I did it perfectly the first time. 224.2251, whatever. I have to round that up to 225. Okay. Good. Part B. If no estimate of the sample proportion is available, how large should the sample be? So now they're basically saying, we're not going to give you a p hat. We're not going to give you a sample proportion. So remember, I told you, if you're not given one and you're trying to figure out what n should be, you play it safe and you use p hat as 0.5 and q hat as 0.5, because that'll basically give you the most error possible. So worst case scenario, you're just covering your bases. And so in this case, n would be 0.5 times 0.5 times 1.65 divided by 0.05. This all gets squared. Punch that in the calculator and you should get 272.3. What do we do with that? We have to round that up to the next nearest whole number, so 273. So notice, if we don't have an estimate for p hat, we would need a larger sample. So 225 when we had a p-hat, and if we don't, 273. Okay, good. So this is telling you the minimum sample size to guarantee the error is less than what they wanted, less than, in this case, 0.05, but your error could always be even less than that. Okay, good. So that concludes all of the confidence intervals. Let's hop into Statcrunch and see how to work with that there. All right, question 1. Given below are the number of successes and sample size for a simple random sample from a population. So X is 7, N is 50, and we're setting it up at the 90% level. So first determine the sample proportion, A, p-hat. We know that's X divided by N. So 7 divided by 50. You can use your calculator. 7 divided by 50. 0.14. And then B, is the one proportion Z interval procedure appropriate? Select all that apply. A, the procedure is appropriate because the necessary conditions are satisfied. Notice they told me here we collected the data from a simple random sample. X is 7, so that's sufficiently large. Remember, N times P or X has to at least be greater than or equal to 5. And the rest say it's not appropriate, but that's not true. It is appropriate. Good. Now, select the correct choice below, and if necessary, fill in the answer boxes within your choice. So the 90% confidence interval, it is appropriate, so we're doing it. So here we go. Get more help. Open up your Statcrunch. And this time we want proportion statistics. So you're going to go to Stat, and then proportion stats. This is just one sample, and we have the summary stats. Number of successes is X, so that's 7. The number of observations, that's N, that's 50. And this time we're setting up a confidence interval at 90% level. And just leave it at the standard walled method. Okay. Compute. They give us the lower limit, the upper limit. So we're going to round to 3 decimal places, 0.059 to upper limit 0.221 if I'm rounding. Good job. Then they want us to find the margin of error. So to get the margin of error, what you do is you're going to find the difference between the upper limit and the lower limit for your confidence interval, and then divide that by 2. That'll give you the margin of error. We've talked about that before. So I'm going to take 0.221, subtract 0.059, upper limit minus lower limit, cut that in half, divide by 2, that's my margin of error. So it's 0.081. And the 90% confidence interval is set up as, remember, it's p-hat plus or minus E. So p-hat, we actually have from up above, part A, it's 0.14, our point estimate, 0.14, plus or minus the margin of error, which is 0.081. And that's it. Okay, you guys should be fine on those. Then I wanted to hop to example 4, question 4. So just because the setup's a little different. It says, in a poll, 800 adults in a region were asked about their online versus in-store clothes shopping. One finding was that 38% of respondents never clothes shop online. Find and interpret a 95% confidence interval for the proportion of all adults in the region who never clothes shop online. Okay, so again, you don't need to open the tables here. We're just going to hop over to Statcrunch, stat, proportion stats, one sample with summary. And notice for number of successes X, they actually didn't give it to us. They gave me here that the sample size N was 800, and they gave me p-hat 38%. So we can figure it out because number of observations is 800. Number of successes is going to be 0.38 times 800. 0.38 times 800, and this is 304. So that's what X should be, 304. And then we need a 95% confidence interval, and we should be good to go. So 3 decimal places, lower limit 0.346, 2 upper limit if I'm rounding, 414. Nice work. Now we need to interpret the confidence interval. So there is a 95% probability that the true percentage of all adults in the region who never close shop online is within the bounds of the confidence interval. No. With 95% confidence, the sample proportion of a survey that asks adults in the region whether they close shop will be within the bounds. It's not about the sample proportion. We set up confidence intervals to see where the population proportion is. With 95% confidence, the true percentage of all adults who never close shop is within the bounds. That one's sounding right. So we don't make confidence intervals for estimates on the sample proportion. We make it for the true proportion, the population proportion. Good job. Okay. So that is everything that you guys need for this section. Let's hop back into the lecture right now, and we'll look at hypothesis tests. All right, now we're moving into section 12.2, hypothesis tests for one population proportion. So the z-test for a proportion is a statistical test for a population proportion. And the normal distribution is used to test hypotheses for proportions. And recall, a normal distribution can be used to approximate the binomial distribution when n times p is greater than or equal to 5 and n times q is greater than or equal to 5. As previously stated, many test value formulas and statistical tests follow this basic format. We have the test value equals observed minus expected divided by standard deviation. And the test value formula for the z-test for a proportion is as follows. P hat, that makes sense, that's your observed, right? Because that's your sample proportion. Minus P, that's the expected, that's your population proportion, divided by standard deviation. The only difference here from when we set up confidence intervals is that we have square root of PQ, not P hat, Q hat, okay, when you do your hypothesis test over N. And for our one proportion z-test, we have the following options for our null hypotheses. You could either have a two-tailed test where P does not equal P naught. P naught is like some proposed value, okay, that the population proportion equals. Left-tailed, right-tailed, and then the rest of it is the same. This textbook doesn't use Q. They like to just keep writing 1 minus P naught, okay, so whatever. And let's go set it up. Here's the option for the critical value approach, p-value approach. I want to do a couple examples here, and then we'll get into Statcrunch. Okay, the percentage of physicians who are women is 27.9%. This is just stated like a fact, so that's what it's believed the population is, okay? In a survey of physicians employed by a large university system, 45 of 120 randomly selected physicians were women. So that's coming from a sample. Is there sufficient evidence at the 0.05 level of significance to conclude that the proportion of women physicians at the university health system exceeds 27.9%? Ooh, okay. So let's see here. Our null hypothesis always involves equality. In this case, it's not mu, it's about a proportion P. And they're claiming that 27.9% of physicians are women. So change that to a proportion, 0.279. Okay, you don't use the percents in the hypothesis test. And then the alternative, I'll put A this time. Notice here they say, is there significant evidence to conclude that the proportion exceeds 27.9%? So we're proposing or claiming that it's greater than 0.279. That's where the claim is. Good? Okay. So if P is 0.279, then Q is 1 minus 0.279. So that's 0.721. And then let's just list everything they gave us. Also, I can get P hat. P hat is going to be 45 out of 120. And that's 0.375. Okay, save all of that. We're going to need that in a hot second. Decide on the significance level. I don't get to decide. They told me. Here it is, 0.05. So alpha is 0.05, and this is right-tailed because the alternative hypothesis involves greater than. Yes, we're proposing that P is greater than 0.279. Okay, now we're going to compute the test value. So I'll rewrite the formula. Z equals P hat minus P over the square root, and I like using Q instead of 1 minus P, so PQ over N. So in the numerator, we will have P hat, that was 0.375, minus P is 0.279, that's the proposed proportion value, over square root, and then make sure you don't use the hats in the bottom. It's just PQ. So 0.279, 0.721 over 120 over N. Yes, N was right here. Let me write that explicitly for you. Okay, then do all this in the calculator. Punch it all in there, and you should get 2.345. So that's our test value. Okay. Now we need to find the critical value. So again, you might have memorized these. If not, you can just find them in Statcrunch. If you go backwards, right? So you pull out your normal distribution, and then since the test was right-tailed at the 0.05 significance level, you put that probability in for just that right portion, and then it will give you the Z value, which is 1.65. Okay, so that's my critical value. And now we need to make the decision to reject or not reject the null hypothesis. Well, where does the test value fall? The test value was 2.345. That's way over here. It's more extreme, right, than our critical value. This is the critical region over here. Another name for it, remember, is the rejection region. So that means our decision is to reject H naught. Okay, and then we're going to summarize our results. So we'll say there is, because we chose to reject the null, sufficient evidence to, and then remember, you either say support or reject as the next word, and since the claim was in the alternative, then we say support the claim that the proportion of women physicians at the university health system exceeds 27.9%. Okay. All right, so we cranked one out by hand. Now let's hop into Statcrunch. I'll show you how to do a hypothesis test in there. All right, so here's a hypothesis test for one sample proportion. In 2010, shortly before a country's midterm elections, people in that country were dissatisfied with government, and 53% of adults in the country thought that a third major party was needed. In a recent poll, 56% of 1,158 adults in the country felt the same way. At the 10% significance level, do the data provide sufficient evidence to conclude that the percentage of all adults in the country who now think that a third major party is needed has changed from that in 2010, use the one proportion z-test to perform the appropriate hypothesis test. So first, what are the hypotheses for the one proportion z-test? Notice here, they want us to see if there's sufficient evidence that the proportion has changed from that in 2010. So that's what the null is going to deal with. What was the believed proportion in 2010? And that was that 53% of adults thought a third major party was needed. So P is equal to 0.53. Okay, always change that to a proportion. And here in the alternative, all they're saying is that it has changed from that in 2010. So not more than, not less than, just not equal to, not the same as, that it's changed. So not equal to 0.53. Fantastic. Okay, what is the test statistic? So now what we're going to do is go ahead and get that Statcrunch rolling. And this time, again, we're going to pop into proportion stats. It's a little too big. Let's make it a wee bit smaller. Okay. Proportion stats, one sample, and we have with summary, right? We don't have raw data or anything going on here. Okay. Then let us see the number of successes. Okay, again, they didn't give us that. They told me in this recent poll, this is the sample, there were 56% of 1,158 adults. So the number of observations was 1,158. And the number of successes, that it's 56% of n. So I'm going to take 0.56 and multiply by 1158. And that is 648.48. Okay. And then perform hypothesis test that P is equal to 0.53. Alternative is that P is not equal to 0.53. So we should be ready to go. So what is the test statistic? 2.045491. We're rounding to 2 decimal places. So that would be 2.05. Good job. Thank you. And then the p-value 0.041, right? If we're rounding to 3 decimal places. Oops, 0.041. Good. And then what is the correct conclusion? So alpha, where was alpha? 10% significance level, so that's 0.1. And the p-value is less than alpha. When p is less than alpha, we reject the null. And we say the data do provide sufficient evidence. Small p-value, strong evidence that it has changed. Oh no! What did I do wrong? Oh, I clicked do not. Oops, I should have read it more. The data do provide sufficient evidence. Good. Okay, so that's it. You guys should be okay on these hypothesis tests. Okay, last section in this chapter that we're going to cover is 12.3, Inferences for two population proportions. So the z-test for two proportions is a statistical test for comparing two population proportions. Here are our assumptions. First is that we have simple random samples, and the samples must be independent, meaning no relationship exists between the subjects in each sample. And then N1, P1, N1, Q1, N2, P2, and 2Q2 are all greater than or equal to 5. Why? Well, this is related to the rule of thumb for when we can use the normal distribution as a good approximation to the binomial distribution. So that basically just tells you, hey, your samples are large enough for you to proceed and use the normal, use a z-test to approximate here the distribution of these variables. And the test value formula again follows the same basic format. You have observed minus expected divided by standard deviation. Okay, the test value formula for the z-test is in this following format. So you have P1 hat minus P2 hat. Those are both of your sample proportions. Okay, we have two samples here, minus P1 minus P2. This is always going to be 0. because in the null, we just assume they're equal, over square root of p bar q bar times 1 over n1 plus 1 over n2. What the heck is p bar and q bar? P bar is basically you take all your two samples and combine them into one, and p bar equals x1 plus x2 divided by n1 plus n2. And then once you have p bar, you just find q bar by setting up 1 minus p bar, okay? So you can set up confidence intervals and perform hypothesis tests for two proportions. And this is just summarizing the assumptions that your textbook wants. And then there's the formula. Again, this gives you the standard error here, but they set it up a little bit differently. So I'll show you kind of how to do it by hand, and then we'll hop into Statcrunch. I just think the 1 minus looks so messy. I don't love the way they write things out. Okay. Bullying is a problem at any age, but especially for students aged 12 to 18. A study showed that 7.2% of all students in this age bracket reported being bullied at school during the past 6 months, with 6th grade having the highest incidence at 13.9% and 12th grade the lowest at 2.2%. This is an old study. My goodness, I wonder what it would be now. To see if there is a difference between public and private schools, 200 students were randomly selected from each. At alpha equals 0.05, can a difference be concluded? Oh, I meant to highlight. Can a difference be concluded? Okay. So we want to see if there's a difference between public and private schools. Okay. So let's go ahead and see here. Since they mentioned the word public, I'm inclined to call that P1 and then private P2, but then when I look at the data table, they have them the other way, so whatever. I'll call private 1, or sample 1, population 1, public 2. Okay. State the hypotheses and identify the claim. So the null is always going to be that P1 is equal to P2, or you could see it that P1 minus P2 equals 0. Remember, that's another way we write it. And then the alternative is that P1, in this case, just a difference means that they're not equal to P2. Or remember, we could write P1 minus P2 is not 0. And the claim is right here in the alternative. Okay, let's decide on the significance level. Well, they told me it's 0.05, and this is a two-tailed test. And then we have to compute the test value. So before we do that, we need a few things. We need P1 hat, we need Q1 hat, we need P bar and Q bar. So P1 hat, remember, I'm calling private schools population or sample 1. So that would be 13 out of 200, which is 0.065. You know what? I don't need Q1 hat. I just need P2 hat. So that would be, for public schools, the proportion of students bullied, 16 over 200. And that's going to be 0.08. And then to get P bar, what you do is you add up the x's for each of those samples, so 13 plus 16. And then you divide by the total sample size of both, so 200 plus 200. In this case, they were equal. They're not always equal. So divided by 400, and this gives me 0.0725. And then Q bar is just 1 minus P bar. So this is 0.9275. All right. Okay, good. So let's compute the test value now. So the formula was P1 hat minus P2 hat. So 0.065 minus 0.08 minus P1 minus P2 is always 0. That's always going to be the same. Over, and then you have square root P bar 0.0725. Q bar 0.9275 times 1 over n1 plus 1 over n2. Just throw this all in the calculator and you should end up with negative 0.578. Okay, good. Did you get the right number with your calculator? If not, maybe I need a calculator tutorial class. We can live stream if you join my Patreon. Okay, find the critical values. So alpha is 0.05 and the test is two-tailed. So let's see. Do you remember what it is? If it's a two-tailed test, then you set up the same value that you would with the confidence interval. It's going to be plus or minus 1.96. So we've got two critical values because this is a two-tailed test. And then we got to make the decision to reject or not reject the null. So where does the test value fall? In which region? Negative 0.578, that's somewhere around here, right? Negative 0.578. And this is the non-critical or non-rejection region. So that means our decision is going to be that we fail to reject H naught. Okay, good. So now let's summarize there. In this case, I'm going to say is not, since we failed to reject the null. Sufficient evidence. Two, should I say reject or support? Where was the claim? In the alternative. So I'm going to say support the claim. That, what were they claiming? There is a difference in reported bullying. I think that word reported is important. How much bullying goes unreported? Between public and private schools. I am a child or a product of the public school system. I have no frame of reference for what happens at private schools. Very curious. Okay, so let's get into Statcrunch, see how we can do these hypothesis tests there, as well as, you guys, confidence intervals. You can do it all. How exciting. Okay, so let's look at these two sample proportion hypothesis tests and confidence intervals. So question 11, the number of successes and the sample sizes for independent random samples from two populations are provided for a right-tailed test. Use a 90% confidence interval. Okay, so determine the sample proportion P1 hat. P1 hat is going to be X1 divided by N1, 19 divided by 50. Okay, 19, it should be 0.38, right? Right. Correct. Okay. How did I know that? I just doubled 19 and doubled 50, and it became 19 out of 50 is the same as 38 out of 100, which is easier to think of, right? And convert to a decimal in your head. Okay. Next one, P2 hat, that's going to be 11 divided by 100. Do you know how to do this one in your head? I hope so. 0.11, right? We didn't even need the calculator. Okay, good. Nice. Now determine the pooled sample proportion. Okay, remember they use P hat. I did P bar in the lecture notes, whatever. So you're just combining everything into one big sample. That's what that pooled sample proportion is. So you add up X1 and X2. So 19 plus 11, that's going to be 30. 30 divided by 150. Ooh, can you do that in your head? 30 divided by 150. It's the same as 3 divided by 15. Which means it's 1/5. So it should be 0.2. Yay. Good job. Okay. Decide whether using the two proportion Z procedure is appropriate. Well, they told me in the beginning, we have independent and simple random samples. The size is sufficient, N times P, or if you just look at X1, X2, they're greater than or equal to 5. So everything's fine. We can go ahead and perform the procedure. And now we're going to set up a z-test. Okay. The null hypothesis, I mean, get out of town with this inequality. We know it has to have equality, right? Now let's just see between C, E, and F, which one has the correct alternative. And notice in the directions here, they said we're doing a right-tailed test, which means P1 is greater than P2. So that's F. Like I said, check it, please. Good. Okay, now we need the test statistic, if appropriate. Yes, it's appropriate. So let's get Statcrunch rolling. And then this time you're going to select to sample. That's the only difference. So stat, proportion stats, to sample with summary. So sample 1, you're going to enter X1, that's 19. Number of observations N1 is 50. Sample 2, X1 is 11. Number of observations 100. And then remember, they just set up the null and alternative a little differently. So P1 minus P2 equals 0. And then this one's right-tailed. So P1 minus P2 greater than 0. All right, and compute. And here's our z-stat, if we're rounding to 2 decimal places, that's going to be 3.90. Okay, so let's scroll this down a wee bit, 3.90. Good job, I know. And then the p-value, it's less than 0.0001. If we're rounding to 3 decimal places, those are all going to be zeros. It's a little weird, but whatever. It's a tiny, tiny p-value. So at the 5% significance level, remember, small p-value less than alpha, reject the null. So it's either A or B. And the data, it does provide sufficient evidence. So A, do provide. Check your answer. Nice work. Okay, now they want us to set up a 90% confidence interval. And you guys, so you don't have to re-enter everything. Check this out. You go options. Are you ready? This was exciting for me. Edit. Bam. Then it saves everything that you already entered. Then you're just going to go over here and switch it to a confidence interval at the 90% level. Compute. And we're rounding to 3 decimal places. So lower limit is 0.146. And then upper limit will be 0.394. And that's it. That's it for question 11. Question 12 is just a confidence interval. You guys should be ready to go, no problems. And that actually wraps up chapter 12. So stay tuned. We're going to jump into chi-square distribution, goodness of fit test in chapter 13. Exciting stuff. Give the video a thumbs up if you haven't already. Subscribe, Math TV with Professor V, and I'll see you guys soon.